Now in the app, we're going to switch to slightly more technical and formal material. I'll start with the idea of convergence. Let's say we've got an infinite sequence of numbers, and as we add more and more terms and we get a series, adding more and more terms, we create what are called partial sums. First thing we have to do is show that those partial sums are approaching some limit. We've talked about limits, even if we don't know what that limit value is. Now, beyond that, if the sequence of numbers is generated from some function, and we can input a range of different values, maybe all real numbers or all positive numbers, and that generates for each input value a different sequence of numbers, and the partial sums of each of those sequences have their own limit values, then we say the series is converging for the input values. Why is that idea important? Is first of all, it enables us to confidently state that there is an exact value for numbers such as pi and e and ln2 and the trigonometric functions. Then it enables us to compute finite values as close as we like to those limits. And all of this underpins calculus and much of modern mathematics. So in this table, it's given the infinite series that generate the same values as functions that we are familiar with, such as the exponential function, the sine function, the ln function, but the natural logarithm of 1 plus x. But in addition, the table says, without justification, it just states it, which values we can input so that the series will generate the right output value. And we can see for the first three that it converges for all real x's. But for the ln, it's much more restricted. And that particular sequence of partial sums only converges when x lies between -1 and 1, and so on. And there's an indication of what we call Taylor and Maclaurin series, which are a way of generating those series expressions that relate to the original function. And that's gone into more detail in module 16. When we started off talking about limits and the use of the epsilon value as a way of demonstrating that a sequence was approaching a particular limit, say we don't know whether a particular sequence has a known value, there are different tests that we can use, either to find out what that limit value is, or just to indicate a limit value exists even if we don't know what it is. So the first one is direct, where we can do a bit of algebra and then find out what the limit actually is, because we end up with the limit value plus some other expression that we know via previous work as a limit. So for example, 2n plus 1 divided by n can be rearranged to 2 plus 1 over n, and as n gets larger and larger, a positive integer, we know it approaches 0, so the sum itself approaches 2. The next one is the monotone convergence series. If we have a sequence of numbers, because at the moment we're just talking about sequences, and those values are increasing, so each subsequent value is larger than the previous one, but somehow we know that the sequence of numbers is bounded above, and that bound may be much higher or greater than the limit, or that the sequence of numbers is decreasing and we know that there's some value that's less than or below every value in the sequence, then we know that the sequence will be converging, even if we can't explicitly calculate what that sequence is. Then there's the squeeze theorem, that if we've got a sequence that we can show that every term at a particular position in the sequence lies between the terms in two other sequences, and those two other sequences, one whose values are below and one whose values are above our sequence of interest, and both the bounding sequences approach the same limit, then the sequence we're interested in approaches the same limit. Then we get more powerful tests and more widely applicable tests, the Cauchy criterion, whereby we say if we've got this epsilon or small error value, and that we say the difference between every pair of terms is less than this epsilon value, where the terms are at some position in the sequence beyond a given value n, then that means that the terms in the sequence are getting closer and closer to each other. The ratio test for terms in a sequence takes a term and divides it by the previous term. And the test is, if as n gets larger and larger, the limit of that ratio is tending to a fixed value r, then depending on the value of r, this will tell us if the sequence reaches a limit. And this is particularly useful when the series is defined in terms of factorials or exponentials. And the rule is, if that limit ratio lies between 0 and 1 but is not equal to 1, then an, the sequence, will tend to 0. If that ratio has a limit that's greater than 1, then the sequence will tend to infinity, it will diverge. And if that limit ratio is equal to 1, then it's inconclusive. You can't use this test to determine whether the sequence will converge to 0 or diverge. And there are 4 examples given underneath. Some tend to 0, 1 diverges, and 1 is inconclusive. Remember, you must take a term in the sequence and divide it by the previous term and work out the limit of that ratio as n tends to infinity, and compare that value r against 0 and 1.